One moment. Okay. So far we discussed some fundamentals of organic chemistry, right? To understand the hybridization, structure, and bonding, followed by resonance, electronegativity, dipole moments, inductive effect, acid basicity, and functional groups. So basically, my objective was, to connect one by one, because if we don't know electronegativity, then we'll not able to understand the dipole moment. That's why this is the sequence I followed, and I explained all those stuff using examples, right? So, but still we have PowerPoints. We'll discuss a few more stuff, okay, from PowerPoints. And do you guys have any questions before we start? Anybody any questions? Like, I mean, if you have facing any troubles or any like problems you have understanding materials or anything?
Yeah.
Yes.
So I can't remember which question it was on that like example quiz you had, but it was the one where the answer was 2, 4, 6, 8, like where the um, electrons like
Okay, I
moving.
understand. I understand the negative charge, position negative charge. Okay, so I'll discuss this one later. Okay, I mean before the quiz, I'll discuss that one. Okay, and
Okay.
I have one. Yeah, so no worries, I'll discuss that. Okay, so I just have one announcement that this, like, but students who suddenly disappeared last lecture. So the thing is, I have my own strategy that how I manage those things, and if you stay away from me, I don't know that you are learning or not. So that's my humble request, that please attend the at least class. How many hours? So whole semester you have 36 hours and 40 minutes. At least spend this much time. You already selected, right, this course, and please spend time with this subject, at least minimum time. So don't be disappear, because if you don't understand one of the concept, then next level you will have some difficulty. So please try to attend the classes. Okay, so that's my um, okay, so we'll start a quiz after some time. Let's discuss, let's see if we learn something. Okay, and okay, so if we have a molecule, nitrogen, now here you have hydrogen and one lone pair over this nitrogen, and you have double bond over here. So this is called imidazole. Okay, so if we understand those concepts, whatever discussed, then the concept is which one is this nitrogen, let's say 1, nitrogen 2. Okay, what is the hybridization of this nitrogen, and what is the hybridization of nitrogen 2? What is the hybridization state? Anybody want to try? What is the hybridization of 1, nitrogen 2?
Would nitrogen 1 be sp3 and then nitrogen 2 would be sp2?
Okay, so that is expected hybridization, because based on the bonding, we can see that nitrogen has 3 bonds, sigma bonds, and 1 lone pair. So nitrogen, you have one lone pair 3 sigma bond. That means we know that 3 sigma plus one lone pair, that means sp3, right? But this is expected hybridization sp3, but we have some expectation. So this is not really sp3, but this is again sp2, because based on our so far our discussion, we know that this nitrogen sp3, right? But that's not really, so the hybridization is not sp3, the actual hybridization is sp2. Okay, so actual. So how will understand, how will describe this one, that the nitrogen one is sp2, right? That's the question. Okay, so even not only this particular example, if we have another example, let's say if we have furan, oxygen, again this is oxygen, you have two lone pair. Now again you can think that what is the hybridization of this oxygen. So expected sp3, but it's not actual sp2. Okay, now how we can explain why it is and how we can visualize, understand that actual hybridization is sp2, not sp3. Okay, so that if we want to understand that, we have to have orbital diagram. First, if you see the nitrogen, how much? Nitrogen means 7 atomic number. That means you have 1s2, 2s2, and 2p3. So now if we do electrons, if we give electron, that means there are 2 electrons, and here you have 3 electrons, right? This is a ground state. But if you have excited state, that means the electron will go over the excited 2p orbital. That means we'll have 1, 2, 3, 4. Now if we make a hybridization, then what we get? We get this one, right? 1, 2, 3, 4. So 1 electron, 2 electron, 1 electron, 1 electron, right? So based on that, if we do sp3, okay, sp3, then what is the shape of the orbitals? So if it's sp3, that means we have 1 lobe, second, third, fourth. And now we can see that, okay, hybrid orbital contains 1 electron, and one of the lone pair contains, one of the orbital lobe contains a lone pair, right? So this can make sigma bond, this can make sigma bond, and this one can make sigma bond. So you can have 3 sigma and 1 lone pair. Example, nitrogen, right? Okay. Now, just think about how we can do sp2 over here. Let's say if we have 1, 2, now you have 3 electron over here and lone pair over here. If that is the case, so this is the orbital in pure pz orbital. So in that case, if we draw the orbital, what we'll see that, okay, so if it sp2, that means you have 3 hybridized lobe and you have 1 unhybridized lobe, right? That means this is the pz, which has a 2 electron lone pair over here, and now you have 3 electron over here. That means these 3 will make a sigma, this one sigma, and this one sigma. So now the lone pair in pure p orbitals. Okay, that's the one case. Okay, that's the one case when you have, okay, so that means you can see that 3 sigma 1 and 1 lone pair, which is pz. Or other case, if we have this arrangement of electrons, let's see, if we have this one, 1, 2, 3. Now here in pz you have 1 orbitals. So if that is the case, then how we represent the orbitals? We represent orbitals here 1 electron, and you have 2 electron over here and 1 electron over here, right? So what is the difference? So this part, what is the difference between these 2 cases? This one and this one. You can see both of them actually sp2. What you said, both of them are sp2. So this is also sp2, and this is also sp2.
I think you muted yourself, Professor Mana. Yeah, I can't hear
Yeah.
anything.
I can't hear him. Yeah, I can't hear him either.
Dr. Manna. Dr. Manna, we can't hear you.
He's frozen.
He's going off.
Wrong?
Everybody click on the raise your hand thing, and then maybe he'll see it.
I don't have that option.
If you click reactions on the bottom right, there's a button in there.
I think he.
I think he can definitely hear us. He just is trying to fix it.
Yeah, I think it's his computer.
No, I don't think he can hear us because I think he would have fixed it.
He's still talking.
Is he?
Like you can see him in the little camera thing.
Someone want to like call him?
Like, he probably doesn't hear us.
Just need him to look up.
Yeah.
He's focused.
Is there not a chat? I thought there was a chat.
No, he turned that off.
Yeah, there's no chat feature.
If we all do like the clapping thing under reactions.
I just called him, but I'm sure his phone is off.
Fantastic.
How you guys feel about the quiz?
Bad.
Kind of
Yeah,
not very
I
good.
don't know.
Not good.
Well, he drops the two lowest ones, so there's that.
I'm neutral.
Is the quiz during class?
Yeah, it's the last 20 minutes.
Do y'all know how we submit the quiz?
No clue.
I think he makes a link available only for that time.
I think it's on Blackboard, so it's like a normal quiz.
I thought it was a group me quiz.
No,
You can do quizzes on GroupMe?
it's on Blackboard. But
The
like,
quiz one isn't on Blackboard.
he's gonna put it there.
He
like,
hasn't
when it's
made it
time.
active yet.
Lovely.
And then we just stay on Zoom and he watches.
Yeah,
Oh, I think he's
usually it was
looking at
through
us.
McGraw-Hill, I think.
Keeps looking at us for like us to respond or something every time.
Dr. Mann, we can't hear you.
Okay, yeah, I think he's finally noticing we can't hear. He can't. Like, there's no people.
Yeah, like is he not? Should we raise our hand again? Oh, it's still there.
Can you guys hear me now?
Yes.
We can.
Yeah. So we missed quite a lot, I'm sure.
Okay, so that means now we can see that if we represent this molecule, you have here nitrogen, and you have nitrogen over here. So now the lone pair is here. So that means if you think about here, so that means it's parallel to the p orbitals over here in this carbon. That's why this can participate in the conjugation, right?
Dr. Mann,
Yes.
we probably lost you for about 3 minutes. So is that the stuff you just covered when we couldn't hear you?
Yeah. So basically, I was talking about that 3 different cases you can see for sp nitrogen sp2 hybridization, right? So lone pair can be either in pure p orbital or it can be in a hybridized orbital. So depending on that, you can see that you have to count then this particular case the total number of pi electrons. So pi electrons equals to here 6 pi electron, right? So although you can see 2 pi bond, that means you have a 2 pi bond means 4 pi electrons, but we have to consider this lone pair of electrons as a pi electrons, okay? So that's why this is the case, and a similar case over here for oxygen. You have to count these 2 electrons, okay, because they are in pure p orbital. So if they are pure p orbital, they can conjugate with the p orbital and its double bonds, okay? Any questions?
So does it depend on how it's arranged, where it counts as as pi bonds?
Yes, so if you have an adjacent carbon, oxygen with pi bonds, that means the molecule itself hybridized to sp2 so that it can participate in the conjugation lone pair. So lone pair comes over p orbital instead of hybridized orbital. Okay.
So the difference between just like a regular sp3 hybridization for like ammonia is when there aren't any double bonds, and for this case, because there are double bonds, that's why it's sp2.
Yes. So when you have at least one pi bond, that means that is sp2 confirmed, right? But when you have a nitrogen adjacent carbon is sp2, you have a double bond. In that case, this nitrogen or oxygen will be sp2 hybridization. I mean, it looks like sp3, but the lone pair will be on the pure p orbital, so that it can participate in the conjugation with the neighboring pi orbitals, right? Make sense? Okay, so you have hydrogen already there. Okay, so hydrogen should miss. Okay, so this is a case. This is one kind of like difference in hybridization exception that you have to remember. Actual hybridization of those molecules. Okay. Okay, so that means last time we are talking about hybridization, right? So here. Okay, so we have to know a few more things that if we have hybridization, then you have sp3 hybridized orbital. So then what is the like possibility that hybridized orbital can make a sigma bond only? So hybridized orbital will not participate in the pi bonding. So if you want to have a pi bonding, that means you have to have a pure p orbitals. Okay, that's the one criteria, here. Okay, so next, so based on the hybridization, and we can think about that. How many bonds you have. If carbon, if you have 4 sigma bonds, that means as sp3, right? Or if you have 3 sigma 1 pi sp2, or if you have 2 sigma 2 pi, that means sp hybridization, right, for carbon. So we have to like, by looking at the molecule, you have to understand that what is the hybridization of carbon, oxygen, and nitrogen. So these 3 atoms we have to understand completely. Okay, so here's one example that you can see. So nitrogen, on lone pair over here, so you have 3 hybridized lobes, so they can make a sigma bond with the hydrogens, right? And the lone pair over here. Okay, so this is unshared electron pair. And like example here, water. So water here, you have a 2 lone pair, right? So then what is a bond angle? That's the important thing. What is the bond angle? So we have to understand that for bond pair repulsion is less than the bond pair lone pair repulsion, and a lone pair repulsion is greater. So then that means in water, if you have a 2 lone pair repulsion, the bond angle will decrease. Okay, because of the higher repulsion in between 2 lone pairs. So that's the difference from methane to ammonia to water. That bond angle will change. So ideally, we know that the bond angle for methane is 109.5. Because of the presence of lone pair, now bond angle will change to how much? It's 107, right? And for water, 105. So bond angle decreases because of the presence of lone pair bond pair repulsion, or here lone pair repulsion. Okay. So here you can see the example, this one. So it's an example of methane. So that means you have sp3 means you have 4 lobes, 4 hybridized lobes. So each of them can participate in a sigma bonding. Okay, so one of the lobes make carbon sigma bond, and other 3 lobes make carbon hydrogen sigma bonds. Okay, so that's the only possibility for carbon, can make only sigma bonds when it is sp3 hybridization, right? So that's the example of methane. And okay, so next. So when you have a carbon-carbon single bond or sigma bond, so this bond rotation is possible. So if we have a bond rotation, we can have 2 different conformers, but this bond rotation is not possible for sp2 or sp3 carbon. Like if you have multiple bonds, let's say double bond or triple bond, that bond rotation is not possible because of the pi orbitals overlapping. Okay, so make sure we have that information, because we have to use that concept over stereochemistry, that CC single bonds can rotate. Okay, but CC double bond, triple bond never rotate. Okay. Now, so if we have sp2 hybridization, then what is the bond angle? So the bond angle over here 120. So 360 divided by 3, so 120. So the bond angle for sp2 hybridized, all those bond angles are 120 degree, and the geometry is a planar. Okay, so sp2 hybridized orbital is a planar orbital. I mean geometry is planar. Okay, so okay, that means try to visualize that orbital where the orientation of orbitals. So you can see that this carbon over here. Okay, so here, so this carbon, you can see that 3 lobes in one plane. Okay, so 3 hybridized lobe in one plane. So one over here, and one this direction, and one with the carbon. So these 3 are in one plane, and this is a lobe which is perpendicular to those 3 lobes. Okay, so that makes 3 sigma, and this is overlapping lateral overlap. We call pi bonding formation. So that means here you can see that's the overlap pi bonding. Okay. So as you mentioned that carbon-carbon single bond can rotate, but carbon-carbon double bond rotation is not possible. Okay, so that means if you think about this particular compound, that carbon-carbon double bond, you have 2 hydrogen, and here you have 2 different atoms. So basically, if we rotate this bond, then we can expect that okay, oxygen should come over here, but that's not possible. So carbon-carbon double bond rotation is not possible. Those information we have to remember. And now, if we have sp3 hybridization here for acetylene, so this is the what is the bond angle over here? So here bond angle is 180 degree, and it's a linear. Okay. So that means if you look for the orbital, orientation of orbital. So if it is a sp hybridized carbon, that means you have 2 hybridized lobe and 2 unhybridized orbitals. So two hybridized lobes of this sp hybridized hybridization, so they can make sigma bonds. As I mentioned, that hybridized orbital can make sigma bonds, but if you have unhybridized orbital, they will make a pi bonds. So for sp, you have 2 unhybridized orbitals. So that means in sp you can have a 2 pi bonds. That's why you can see for acetylene over here, the carbon 2 lobes make a 2 sigma. So one is carbon hydrogen sigma, one carbon carbon sigma, and other 2 are pi. So if you have multiple bonds, if you have like double bond, triple bonds, you have to know that if multiple bonds, if double bonds, one of them sigma, one is a pi. And if you have triple bond, that means one sigma, other 2 will be pi. Okay. So here is the representation. We can see. So previous diagram, we just represented only sigma bonding, how orbitals overlap. But here we can see, now we know that 2 sigma there, carbon, hydrogen, and carbon, carbon. Now we can swing the p orbitals. So you can see two unhybridized p orbital. Now they can have 2 pi bonds, right? So here you can see the blue lobes, so pure p orbital one way, and the red orbital, so they another pure p orbital, another pi bond. So that means you can think about that. You can visualize that how we can have a 1 sigma and 2 pi if it is sp2. Sorry, it is sp hybridization, right? Okay. Okay. So that means think about that orbital. So we are not able to see here that the orbitals are overlapping, but actually these 2 orbitals will overlap, and that makes a pi bond. And for pi, I mean pi orbitals, so those electrons are freely loosely bonded. So that means lone pair of electron and pi electron, those are not tightly bonded with the nucleus or both the nucleus or in an atom. So they can easily move from one atom to another atom in a molecule. If we have the neighboring pi orbitals, then electrons can move from one atom to another atom. Okay, that's why we see the resonance basically for pi electrons or lone pair of electrons. Okay, but sigma electrons, so each bond means carbon carbon, you have 2 electrons. So we are not talking about those electrons are strongly bonded. Okay, those bond pairs are they are strong, or here carbon hydrogen 2 electrons. So that means we should remember always that for pi electrons or lone pair electrons, they are loosely bonded to the nucleus, so they can easily move from one atom to another atom. Okay, that means here is the summarization that we have to remember: sp3 bond angle 109.5, sp2 120, and sp 180. So in terms of carbon, this is also applicable for oxygen, nitrogen and oxygen, but their bond angle will be different because of the presence of lone pair. So as I mentioned that lone pair repulsion is greater than lone pair bond pair, and lone pair bond pair repulsion is greater than bond pair bond pair. So those are actually basically comes from Vesper rule, okay, Vesper theory. Okay, so that means we have to remember those bond angles, okay, and now also the bond length. So if you consider CC single bond, CC double bond, and CC triple bond, now where is the bond length longer? So CC single bond is a greater bond length than CC double bond, and now so in terms of bond length, we know that okay, CC single bond is a greater and longer bond length. How about the strength? So if you compare the bond strength, now the bond strength will be greater over here because 3 bonds are there. So 2 nucleus are strong force. So that's why you can think about that. The bond strength will be greater over here. Okay, so there's a few things we have to just remember. Hybridization of a different state, sp2, sp3, and sp for carbon, nitrogen, and oxygen. Okay. Okay, so that means I already mentioned that if we have triple bond, that means the bond length decreases, right? Because you have 1 sigma 2 pi, so strong force. And okay, now how about the length and strength of CH bonds vary depending on the hybridization? Okay, so how this is? So carbon, hydrogen, carbon, sp carbon with hydrogen, and sp2 carbon with hydrogen, and sp3 carbon hydrogen. So where is the like stronger bond? Because we have to understand this particular stuff, because once you're talking about FTIR, we'll talk later for the spectroscopy. So there you have to know the stretching frequency. Okay, so now question is why sp hydrogen, okay, shorter bond length, no, increasing bond strength, okay, yeah, so shorter bond length, right? Then is carbon sp2 with hydrogen. And then the reason is here we can explain this particular concept in terms of S character. So if it is a SP, that means you have 50% S character over here. If it is SP2, that means 33.3%, and if it is SP3, 25% S character. So we can explain this particular bond length strength using S character. That means if we have higher S character, that's more electronegative, so that you can have a stronger bond. And now if we have higher S character, how would I make sense that okay, why the higher S character makes a stronger force? Because S orbital comparing p orbital, S orbital have higher, like S orbital nucleus can pull electrons greater extent than the sp2 or sp3. Okay, that's the reason why we have increasing bond strength, percentage of S character. Okay, so here, so we have to like sometimes remember the bond length. So as you mentioned that CC triple bond has a lower bond length than CC double bond. Okay, you can see 121 picometer. So usually sometimes we represent in terms of angstrom and nanometer. So here here you can see 153. So bond length decreases, right? But how about bond strength? So if bond length decreases, the bond strength increases, right? Okay, so this kind of stuff we have to take care of now. Okay, so we will mention that SP means 50% is character, SP2 means 33% is character, and SP3 means 25% is character. And now we discussed 2 examples in acid base chapter. We can explain the stability of conjugate base using this concept. Okay, so if we have 3 different acid, and if we have a corresponding conjugate base, we can explain in terms of hybridization here the S character. If we have higher S character, that means SP, that conjugate base is more stable than the conjugate base where carbon is sp2 hybridized. Okay, because 33 S character. So that we have to use this concept we are using there. We discuss few examples that effect of S character. Okay, so this one we already discussed. Electronegativity, try to remember some of the values, at least hydrogen, carbon, nitrogen, oxygen, and fluorine and chlorine. So few elements, the order from left to right, electronegativity increases, and from bottom to top, this direction electronegativity increases. So we have to remember that trend. or I'll recommend you to remember the value also. At least carbon 2.5, nitrogen 3, oxygen 3.5, and fluorine 4. Okay, those are based on the Pauli's electronegativity scale. Okay, so as we last time I draw one picture, I showed you that orbital, this is sigma bond. That means there is a overlap of two hybridized orbitals over here. And now because of the electronegativity difference, now this bond is polar or generation of, okay, no. So both are having same electronegativity. So this bond is non-polar. So there is no generation of charge separation. So this is non-polar bond, right? Also here, carbon, hydrogen, both are having almost equal, there is no large difference in electronegativity. That's why this bond also non-polar. So now we understand why this bond is non-polar, this is also non-polar. But if we take an example where we have large difference of electronegativity, so that's I discussed last time, carbon, oxygen. Carbon electronegativity is a 2.5, whereas oxygen 3.5. So when you have that difference, that then we can see that generation of charge separation. So basically, make sure that we are following the trend. We are giving negative charge over oxygen and positive charge over carbon, because electrons are negatively charged particle. So if electrons are more towards oxygen nucleus, that's why you are giving negative charge over oxygen. And if we have this direction negative charge, we are representing the dipole vector towards oxygen. So that means using electronegativity concept, and we can see that the bond can be polar. If we have a non-polar bond, polar bond, based on electronegativity difference. Okay. So if that is the case, so when you have that concept using electronegativity, that means carbon now become electron deficient, because carbon should have octet, using octet rule, carbon should have 8 electrons, in the outer shell, because 4 from carbon and other 4 from other neighboring atoms. But now, if few electrons are, the oxygen is withdrawing electrons from this bond, that means carbon going to be electron deficient. So if carbon going to be electron deficient, we also use another term, that electrophile or electrophilic center. Okay, so when that's the case, we also call electrophilic center or electron deficient center. Okay, so as I mentioned that in quantum mechanics, we prefer to represent those bonds in terms of electron density. So if you talk about electron density, then this bond, the electron density towards more over chlorine, because chlorine is more electronegative than carbon, right? So red area represents the more electron density than the blue area, right? So this direction electron density plot. Okay, all right. So we also last time discussed the water. We have a net dipole moment, so that's why water is polar, because oxygen is more electronegative than hydrogen. So this bond dipole moment, these directions, and this which bond dipole moment, these directions. So combining these two, you have a net dipole moment towards the lone pair. So that's why water is a polar molecule. Okay, so those things have to be clear understanding, polar and non-polar concept, because we have intermolecular interactions and also boiling point, freezing point, boiling point, and melting points. So to explain those kind of stuff, we have to understand that this kind of concept, that generation of polarity in the bond. Okay, but whenever you have like this kind of compound is a carbon dioxide, we know you can have a electron density this direction, so we can have a dipole moment this direction. But when you have dipole moment opposite to each other and equal magnitude, then the mu becomes 0. Although we have individual dipole moments, but net dipole moment is 0. Okay. So what are you have net dipole moment? That's what is a polar, but carbon dioxide 0 dipole moment, non-polar molecule. So whenever we talk about polar and non-polar, that means the polar, the word hidden behind is a dipole moment. Okay? Dipole moment. So also we discussed the inductive effect that last time, the electron withdrawing group and electron donating group. So we have to remember those groups which are electron donating group and electron withdrawing group. So let's say nitro or cyanide, carboxylic group, fluorine, chlorine, bromine, iodine. So these are electron withdrawing group and electron donating group. We have to remember those kind of this table, because if if you want to apply for acid-base theory or next chapter. So we have to remember that, okay? Okay, so last time we discussed about Bonsted-Lowry acid-base theory, and we are not using Arrhenius theory here. We are giving preference Bonsted-Lowry and Lewis theory. So we know that for Bonsted-Lowry acid, that means H plus donor, and make sure that H plus means proton, no electrons. H plus, proton, no electrons, and we call electrophile, or I mean electron deficient species. Okay, so H plus donor is a acid, and H plus ion acceptor is a base. That means think about OH minus and H2 minus. So those are have excess of electrons. That's why they can accept the H plus, and they are actually bases. Okay. Okay. So we already discussed this kind of stuff, and now, okay. So here we have to know like how we represent acid-base reaction and how we use the curve arrow. So here you can see acid and base. So that means you have electron rich center over here, and that is electron deficient. So we have to show arrow from electron deficient, electron rich center to electron deficient center, and that's the acid-base reaction. And once you have remove the H plus, the remaining anionic part we call conjugate base. Okay. Okay. So that means I have shared some example in the current assignment 1. So that means you have to follow this concept, which direction we should show curve arrow, okay, for acid-base reaction, and what is the conjugate base, those kind of stuff we already discussed last time, okay. So this is also an example discussed that ammonia NH2 minus, okay, and here if you take this proton, that means nitrogen previously had 2 bonds. Already you have 1 lone pair electron, but you have 1 excess electron. That's why negative charge. So we have to take care of those kind of stuff. Where we have negative charge, positive charge, okay. If you have excess electron, we also talk about carbocation and carbanion. But for now, make sure that you can identify that how many bonds you nitrogen have, how many lone pair, and why negative charge over here, because you have 1 extra electron. So that means this can take this proton and become NH3, now become neutral, okay? And this, because if you take H plus, that means 2 electrons go over oxygen and become minus, right? So this carbon hydrogen bond, you have 2 electrons. It was neutral in this condition, but when the NH2 minus take this proton, now 2 electrons from this bond go over oxygen. That's why you have a negative charge. Make sure that you have clear understanding why negative charge, why positive charge, this kind of stuff. Okay. Same over here. Hydrochloric acid, HCl, same. So not only negative charge, lone pair can be protonate. Okay. So like oxygen making a bond with H plus, because H plus don't have an electron. But if you want to make 1 covalent bond, you need 2 electrons. So oxygen is sharing 1 electron from nucleus and giving 1 more electron to hydrogen so that it can make 1 oxygen hydrogen bond. And now, so here oxygen become positive charge. If we donate electron, oxygen is donating electron, so oxygen become positive charge. So you have to follow those concepts, okay? Okay, can you guys hear me? Anybody?
So once the hydrogen is taken away by the base, the electrons, like between the bond between the original atom and the hydrogen, goes to the original atom because of the electronegativity. Is that right?
Yes. So yeah, so 2 electrons from the bond goes over oxygen. So now become one electron become extra, right? Because think about this particular bond, you have 2 electrons. So 1 electron from hydrogen and 1 electron from oxygen, and make a 1 sigma bond, 2 electron bond, right? But when you take H plus, that means 2 electrons leaving over oxygen atom. That's why become minus, because now oxygen having extra 1 electron, right? And if we represent the negative sign, that means we are representing 2 lone pair, 1 from oxygen and 1 took from a hydrogen atom. Okay, make sense?
It does. Thank you.
Yeah. And so that means we have to identify that if we have an acid-base reaction, which one is a conjugate base or which one is conjugate acid. As I mentioned that after leaving H plus, the remaining anionic part is a conjugate base. And the stability of conjugate base depends on several factors. Let's say inductive effect, resonance effect, element effect, and one more. Which one?
Is it electronegativity? Isn't it hybridization? Or
Hybridization. Hybridization, yes. Also, we also observed one example, the hydrogen bonding, right? So based on structural features, you can see the strength of acid or base depends on several factors. So we have to consider, we already discussed those examples, right? Okay, so that means we know these things. And with the acid base concept, so electron deficient species we call electron deficient, means we call electrophile. And if we have electron rich system, we call nucleophile. So from this Lewis acid base concept, we come up with two neutron, electrophile and nucleophile. So we have to think about that, okay? And we already discussed that pK value, higher the pK value means lower the acidity, and lower the pK value means higher the acidity. So we have to remember those things. So here is the example, okay? That's the example, morphine. Now, some molecules, so this hydrogen, okay? So this hydrogen, acidic hydrogen, because we have OH bond. So now question is, if we have, how we know that which one is acidic hydrogen? So the molecule, if you see that hydrogen bonded with oxygen, carbon, or nitrogen, so we consider those hydrogens can be acidic, okay? So the morphine here, the hydrogen bonded with the oxygen, so this hydrogen is acidic. Again, you have another center, nitrogen, which is a lone pair. So that means this will act as a, sometimes based on the condition, it will act as an acid and as well as act as a base, right? Because we know that base means which can donate a lone pair of electron, and acid means which can give H plus, right? Two different theory using like Bonstein-Lowry theory and Lewis theory, okay? That means you have to, looking at different types of molecule, you have to identify that where is the acidic hydrogen, right? That I have to find out. Okay, I repeat again, this is important, that hydrogen attached to the oxygen, nitrogen, or carbon. So that particular scenario you have to look for. And also we can see the relative acidity. Okay. Okay, so acid base reaction here. Okay, acid strength and pK. So we know already that higher the pK value, lower the acidity. Okay. And based on the equilibrium, we can represent the equilibrium, K equilibrium, and if we multiply K equilibrium with the water concentration, that gives us Ka, we call acid dissociation constant. Okay, and if we add log over there, we got pK. That's how we get the pK values. So you calculate the pK for different acidic hydrogens, and we can compare the strength. So smaller the pK, stronger the acid. Some example, that means we know that HCl, hydrochloric acid, H plus, right? Carboxylic acetic acid is a acid because you have H. Beside that, you can see acetylene, that hydrogen can be acidic also. It's not like that a molecule to be acid, you have to have a carboxylic functional group. No, that's not the necessity. That any molecule can have a hydrogen, can remove and can be acidic hydrogen, but depends on the pK value that we can compare the strengths. Okay. So we discuss several examples based on that. Okay. Okay, so this one I discussed several examples, that equilibrium, which direction equilibrium will shift. So now we can see the pK value over here 25 for acetylene, but here ammonia pK value 38. And what we know, lower the pK value, higher the acidity. That means this hydrogen can remove faster than here hydrogen from ammonia, and that's why left to right, the production of H plus will be greater than right to left. That's why equilibrium will shift towards right. So this kind of acid-base reaction, I posted several examples last time, that how to identify which direction equilibrium will shift. Okay, so stability of conjugate base, we can also, I mean, if there is a pK value, we can compare, but if you don't have pK value, we can compare the stability of conjugate base. So between these two, so here the conjugate base is more stable. That means if you have more stable conjugate base, equilibrium will shift towards the direction. Okay. Okay, so that's the case. And here, okay, so there are some more effect. It's acidic hydrogen. This is quite acidic. pK value is 25. Okay, so this is acetylene hydrogen we call. So if you have the conjugate base, because of the S character of what kind of S character? 50% S character of this carbon, right? Because this is sp hybridized carbon. Okay, so that those things we have to consider. And okay, so we discussed the 4 factors last time, that how to predict the strength of acids. All right, so this is all we have. And okay, so whenever you have molecule, consider the hydrogen contains the carbon, nitrogen, oxygen, or here electronegative atom, right? So fluorine, oxygen, and nitrogen. So this direction, acidity increases. Okay, from left to right, acidity increases because of electronegativity. Okay, all right. Okay, so here also we can explain in terms of atomic radius. So HF. Okay, so here HF you can see fluorine and hydrogen are similar size, but in HBr, bromine is a larger size compared to hydrogen. Okay, that's the reason you have HBr is more acidic, because the bonds become weak. HBr bond become weak than HF. The reason is control over the control over the bond pair of electrons by the nucleus. So if we have larger anion, that means the Br, that means the bond pair over here less control from that nucleus and bond become weak. That's why if you compare the bond strength from HF, HF fluorine, HCl, HBr, HI, that means HI will be the strongest acid comparing those hydrohaloic acid, HF, HCl, HB, or HI. Hydrogen iodide is the strongest acid. So we have to remember those information. And you know the reason why, because of the dissimilar size of atoms, hydrogen and iodine. Iodine is the very larger size compared to hydrogen. But for HF, both are in similar size. That means both are having a strong control over the bond pair electrons. That's why it's not easily dissociate. That's why you can see pK is higher than the HBr or HI. So that you have to remember. And okay, so here pK mentioned. So lower pK, that means HI is the strongest acid. Okay, so make sure that you remember the strength of acidity, hydrochloric acid. Okay, so these things we already discussed. And this is in terms of inductive effect. That means you have fluorine atom. It can drag electrons from this bond. Okay, so here now you can easily dissociate this bond, right, compared to this one, because you don't have any electronegative atom or groups over here in this long. Okay, and we also explain in terms of, okay, this is a, you can see last time I showed you the arrow. The arrow means this direction electron migrating through bond. So that electron migration not only through bond, it can be through space as well, like through solvent. We have some example, but for now we can see that excess electron over oxygen, they can be stabilized by the electron withdrawing group. I mean, electron withdrawing atom fluorine, right here. Okay, so resonance effect basically we have to see that stability of conjugate base. Okay, so if we can have, so between these two compound, if we remove hydrogen from here, now negative charge over oxygen, and if you remove negative charge over oxygen, so now if we have this is a acetic acid, so if you have negative charge over here, that can conjugate with this carbonyl group. That's why the corresponding conjugate base is more stable, and this is more acidic than that one. And you can see the pK value 4.8, here 16. So if we have a lower pK value, we know that that's a stronger acid. Now makes sense how to use those concepts to explain the acid strength. Okay, now here similar example. Oh, the previous one that you can see the delocalization of electron over the C double bond O. If you have pi orbital, that's possible. Okay, so that's all. And we have one thing left. So hybridization also we described in terms of S character. So you can see comparing these three structure or conjugate base, here you have 50% S character that means the carbon nucleus, easily stabilize the negative charge compared to this one or that one, because S character has more control over the negative charge than the 25% S character over here. That's why, so stability of conjugate base increases this direction. That means acidity will be higher for here. You can see the pK value. So both the thing you can match. One thing you can match the pK value, as well as you can match the concept that why that particular conjugate base is more stable using the S character concept. Okay, so that means to get those kind of stuff, sp3 to sp2 to sp. Okay, and a few more things we have to learn. Lewis acid base theory. So we can explain in terms of electron donor and electron acceptor concept. Okay. Okay, so that's all for today, and we have left few things I will discuss in next lecture, and we'll start a new chapter, spectroscopy. We have two types of spectroscopy: mass spectrometry and FTIR. Okay, so that will start next lecture. So now we'll start a quiz. Okay, so let me, guys, please switch on. Switch on your video so that we can continue. Right. Okay. Anybody any questions? Like basically, there is nothing hard. Just we have to go over the concept, go over the PowerPoint, and the problem I'm sharing over Blackboard. Work on those problems, because those problems are very crucial, because I selected those problems that will give you better understanding. So work on those problems. I know some of you, most of you getting concept, but until you work on problems, you're not able to be confident. So make sure that you work on the problems. And if you meet any difficulties, just let me know. I'll re-explain again and again. Okay. And okay. Okay. So, and once again, my humble request, please spend some time, at least, best 36 hours and 40 minutes. Okay. Please sacrifice. You already selected this course. So if you don't spend this time with this subject, I'll not able to manage, believe me. Because if you stay with the, at least if you spend time, you know what's going on, what kind of questions you have to understand. Okay. So please, okay. And here, in the Blackboard, okay, so Blackboard, left-hand side, you have a quiz. I should open now. Okay, so you can try now. It's open.
The quiz will close at 12:20. I don't think there's like a close date or like time thing, right? Is that correct? Okay.
Time is there, but are you able to access or not?
Oh, I can get into it. It's just like there's no like time limit on it.
Where is the quiz?